One person has, I think Alexander is here to collect one to take to St. Petersburg. Are you here, Alexander? I'll put one to one side, but there are four more. Whoever's hands I see go up first is welcome to... So we'll have to do this 4 times, because your hand was pretty quick. Right, hands down, and we'll do it again. Right. 1, 2, 3. It depends largely on where I'm looking. Right. Okay, I think one of them has to go up here. Good catch. And last one. It's completely unfair, I'm afraid, but I only had room in my bag for 5. So I'm going to ask another question before I start. On the program is a talk on Impromptu, which is quite heavily into dependent types in Scala. That may appeal, but I have another talk about type class derivation. And I don't mind which one I do. I can do either. And I need to decide now. Who would like to see a talk on type class derivation? It's maybe a little bit easier. Who would like to see one on dependently typed Scala? Not many hands went up at all. Why are you all here? I will do the one on Impromptu. It's on the program. If people made the choice to come here rather than the other room, it was probably on the basis of the program. So I'll stick to this one. If people would like to see the talk about my library Magnolia for deriving type classes, come and find me later. I'll be around all day, and I'll be happy to just talk through that talk, and maybe we can find a space somewhere and I can do it later. But ask me about either of these. So today we're talking about Impromptu, which is a library I've been working on recently, but there's only really one idea in this library. It's a small library. The idea is to use dependent types in Scala to make writing asynchronous code easier and safer. And there are sort of 2 sides to this. One is, of course, to make it easier to write, but the other is to make it harder to write code that we could reasonably calculate or work out, analyze at compile time is just not going to work or will potentially be unsafe at runtime. So making the runtime failure cases actually compile failures. That is our goal. And I'm going to use a very simple example in this. Imagine you wanted to have the most simplistic version of grep you've ever used. And what we're going to do is we're going to start by reading a file name from standard input. It's an interactive version of grep. So we read a file from standard input, so read the file name, and then based on that file name we load the file, but we also want to ask for a search string that we're going to use to search that file or the contents of the file to see whether it's there or not. And then using the contents of the file and the search string, we're going to see whether the search string exists inside the file. It's completely trivial what it's doing. It's a very simple example, but it does have one important aspect, which is that the 2 tasks in the middle can be done in parallel. We can be reading the search string at the same time as we're loading the file from, say, a very, very slow hard disk. And we want to take advantage of that. We want to use that opportunity for parallelism where we can. Now in Scala, we might write this using futures. Futures are part of the standard library. And we can construct a number of futures. Hopefully you can see my cursor up there. So we're going to create objects. They're futures. The first one will be to read the file. And now this future will start executing immediately as soon as we create it. It will give the user a prompt, and the user will be able to type in the name of a file. Now, once we've done that, because a future is a functor, we can map across that, and we can sequence the next thing that happens after that. So the search future on this second line here will ask for another search string. So much the same again. We don't actually use the value from the file name when we're asking for the search string, but we need to make sure that's happened. It must happen afterwards. Likewise, when we're reading the file as source, we're mapping across the same future in file, but in this case we do need the name of the file in order to read it into memory, and we get an iterator of strings back from that. So those two, you see, there's no dependency between those, but they both depend on the first future, than the in file. And finally, this is sort of the interesting line. It's where we bring together those two previous futures. And we're going to use a method called future.sequence, which takes... who's familiar with future.sequence? Not many. OK, so this is an important method in the futures library. It takes a sequence or a list of futures of things, and it turns it inside out. It turns it into one future of a sequence of things. And it can only do that when all of the futures inside that sequence have completed. So that is future.sequence, and then we map across this again, because it remains a functor. And using the source value, we check whether it contains the search value. Now, the source value is, of course, an iterator of strings, so the Scala collections library will apply that, check the iterator, check every line, see if any line contains the search string, and return either true or false. The thing I don't really like here is that I'm calling value.get.get. Now this is, for a start, it's verbose, but the big problem is that those gets are a little bit dangerous. They're unsafe. Now one of them is dealing with exceptions. Obviously, when you call certain methods in Scala, they may throw an exception. And I'm going to say that for now and for the rest of the talk, I'm not going to care about exceptions because they are very much an orthogonal concern. But the one that does concern me, and the one I'm going to try to fix here, is the other get, which is the one which assumes that the future has already completed at the point it does this. If the future has not completed, then we will have an exception thrown. This is bad. Now we can look at this code. We're programmers. We can do some visual analysis, and we can see that when we sequence search and source file here, we're mapping across them. So we can look at this and we can know with some certainty that this get is safe. It's fine. There's not a problem here. But we have no protection from the compiler. We could make a mistake where we forget to include search in there. And then when we call this, we may not even have that search string. The user may not have been able to enter a search string faster than the compiler faster than the program was able to read the file from disk. It's very likely, in fact. So this would be a runtime error, and it's one that the compiler is at the moment not helping us with. We can improve on this, or arguably we can improve on this a little bit. So that use of, this is all the same apart from this last result value here. We can use use the map method again. This time we're actually using the resultant value. So we're being careful never to use those get methods. So we're going to agree in advance that we won't use those get methods, and instead we're going to match on the sequence. So remember, we're turning a sequence of futures into a future of a sequence. So this is the value we get. It's a sequence of containing the search file and the source file. But the problem we have now is that when the compiler calculates the type of that sequence, it creates a least upper bound. It works out the least upper bound of the types in that sequence, and consequently, we lose a lot of typing information. It finds the best type for all of the elements, and one of them is a string, one of them is an iterator of a string. So the best type that will satisfy both strings and iterators of strings is anyref, or object, or something. It's not a particularly useful type. We can't do much with it. So in order to make it useful, we have to cast it down to a type we can use. Now we can, again, look at this very carefully. We can see that, yes, that will work, because we know that one is an iterative string, one is a string. it should all be fine. But we're having to do we're using a lot of thought to try to convince ourselves that this is safe. We would rather be a bit more stupid and rely on the compiler to be smarter. Now there's an alternative. There's the for comprehension style. This is maybe more familiar to people who have used futures because it's actually a nicer. The code looks nicer. I think you'll agree. Yeah. Does anyone know any problems with this? Yeah, at the back. Correct, absolutely. It does not run in parallel. A future will start being evaluated as soon as it's created, and if we write it in this way, we won't start reading the source from disk until we've received the search. Monads are for sequencing. This is a for comprehension over monads, and sequencing is not what we want. We want parallelism. Now there are ways of making this more parallel, and if you're familiar with this sort of code, then I'm sure you've... Say again? Correct, yeah. So one solution is to define the futures at the earliest possible time, so based on the things they depend on. Now in this particular example, we could start both of these depend on the in file. So first of all, we've got to get the file name. But we then want to create these two futures at the same time. We can do that in the body using a different operator here. We use the equals operator instead of the arrow. But we have to think a bit harder to do that, and we have to work out when is the earliest time we can create a future. It's more of a push-based system rather than a pull-based. What we would like to say is each of these depends on certain things coming before it, and we want to define at the point we have the dependency what those dependencies are, rather than creating them and running them at what we guess is the earliest possible time. And by the way, at the end of each of these, I'm using a wait.result, which is the future library's way of blocking until the futures have completed. So it blocks once at the end, and we're okay with that. Now, using the library Impromptu, this is how I would write that same code. You can set a little bit more code, and maybe there's maybe these implicit ends look a little bit confusing. If you're familiar with Scala, you haven't seen implicit lambdas. But I'm going to say ignore those for now and concentrate on what is defined here. So we have async values. These are like futures, but they're lazy. This one is very much like a future. It simply wraps a thunk. But search and source both define themselves as happening after another async value. So we've declared, if you like, the dependency in the constructor of that async. And most interesting, perhaps, is the final result, which declares both search and source. So this takes var args, defines both search and source as dependencies of this async. And the code here is very simple. Now, you might have noticed a subtle difference between the way I've referred to source. Here it has parentheses. That gets the value out of it. Whereas here, I'm simply referring to the async value. So that's like .get for future, or .get, or .value.get. But we have just simple parentheses here. You're probably wondering, well, what's the benefit of this? Why is this in any way good? And the more interesting case, as you often find, is not the successful cases, but the failure cases. Now, I can make this fail to compile. I can make it fail to compile by forgetting to declare source in here. Now, if I try and compile this, the compiler will say that I've tried to access the value from source, but it hasn't been declared as a dependency. Now, the dependencies defined here, the after parameters, this actually determines the things that execute in advance of the thunk you see here. That is the means of telling Impromptu what to do at runtime. And it doesn't know, it can't confirm that source has been executed. This async value here has been executed before it attempts to run this. And this is a problem. Now, with many ideas like this in Scala, the way to implement them is, the way people choose to implement them, I would say, is with a macro. And macros can do this. They could look at the body of code, they look at the things you refer to, and they could assert whether what we've done is safe or not. I find macros cheating. We can't reason about macros so easily. We don't necessarily trust the logic that is encoded deep within a macro. But the type system is used everywhere throughout our code. We trust it. I trust it. Sometimes more than I should, but nevertheless, if I can implement the same logic using types, that is, for me, a much better solution to this problem than the alternative. Now, I'm 20 minutes through is that 20 minutes to go or 20 minutes through? Remaining. 20 minutes remaining, and I'm about a third of the way through, so let's accelerate a bit. The way I'm going to make this work is using those implicit envs. Now, these things you saw that I told you to ignore, now we're going to look at them. And these have a type, which is env of something. And implicits in Scala, they when we call that async apply method, when we give it the parentheses, this method requires an env to be in scope. Now, I haven't specified exactly what the type is, but it's an env of something. And the env type here must this must be executed inside the body of this async constructor in order to be able to find an implicit env. So we can only call apply when there is an implicit env in scope, and that is inside these bodies. But we need to look at the types in a bit more detail to understand how that works, why it works, and how we can have it work in the cases that we want to work and fail in the cases when we don't want it to work. So let's explore what types are being inferred here. We get an async of something and string for the first one, something and string for the second. So the type on the right-hand side is very simple. It's the same parameter type that you'd have with a future. It is the return value. And that's all I'm going to say about that. But this type here, the other type parameter of async, is interesting. And I'm going to use this type, not telling you yet what it is. I'm going to use the type to encode the dependency graph. These types might be a little bit more complicated than others you've seen. Now, you can think of a graph, or at least you can think of each node in the graph as being defined in terms of the nodes from which it has incoming edges. Okay? And that is a set. There's a set of other nodes in the graph. It's a set because then the edges don't come in any particular order, and then there is at most one edge going into each node in a graph. Okay, so it's a set. And I want to represent a set at the type level because I'm trying to encode this graph at type level. There's another observation I can make about Scala code in general, which is that any stable identifier, so any val, gives rise to a type, which is the singleton type of that value. The singleton type of a value has only one member, which is the value itself. So if you have a val foo equals whatever, there is a type that's called foo.type that has only one value, which is foo. And this is true of any foo anywhere. It has to be stable, it can't be a var. So we require it to be a val. And I'm going to use these two things we've got along with what I think is probably the most important operation in set theory, which is testing whether an element is a member of a set. That's kind of fundamental to set theory, the element of operation. And the way I'm going to do this with Scala is to use intersection types. So intersection types you may have encountered if you've ever seen a product with serializable. You probably didn't want to see it, but these appear occasionally. An intersection type, A with B, is the type of things which are both A's and they are B's. So an instance of A with B is an A, and it is a B. And if it's not both those things, then it's not an A, certainly not an A with B. But I'm going to claim that these have set semantics. So A with B in Scala is considered to be the same type as B with A. A with B is equivalent to A with B. We have reordering and we have deduplication. This sounds a lot like set semantics. And we note that A is a supertype of A with B, and B is a supertype of A with B, and therefore this looks a lot like set membership. Supertype X is a supertype of Y is like saying, is X an element of Y? Okay, so I've tried to draw an equivalence between what I think is the most fundamental operation in set theory with what is absolutely the most fundamental operation in the Scala type system. And I would take confidence from aligning these two things as similar. I'm quite happy that I've been able to identify that they have certainly very similar semantics, and I haven't had to use a very complicated encoding for my set operations based on complicated Scala types. It's absolutely fundamental to everything the type system does, working out whether something is a subtype of something else. So we're going to use intersection types of singletons. This may sound crazy because if you have a singleton type foo.type and another singleton type bar.type, and you take the intersection type of those, that's foo.type with bar.type, it's all the things which are foo.types and which are bar.types, which is absolutely nothing, of course, because only foo is a foo and only bar is a bar, and nothing is both of those things. But that actually doesn't matter, because types are different from sets. This is not equivalent to the empty set or the empty type, nothing, or the bottom type. It's still very useful for the compiler to work with this type, even though it has no instances. We can still use it for driving implicit search. We can use it as a bound on other types. So it's still useful for the compiler to work with it, and we're going to take advantage of that. And these types are going to appear in the first parameter of our async type. And the interesting one is where we create the intersection search.type with source.type, indicating that those are the incoming edges to that particular node in the graph. And both of those are prerequisites of this type, encoded in the type, not merely in runtime values. So, as I said, source.type is always a subtype of search.type with source.type. We know that. But if we were to wrap it in some other type constructor, env, this is not necessarily true. It might be true, and that the times when it's true is when the type parameter of env is covariant. So wrapping a sort of covariant wrapper around a type maintains the subtyping relationship between them. And this turns out to be what we want in this particular case. We want to have that subtyping relationship maintained when these types are mapped, are wrapped, should I say. And we indicate that with a little plus sign on the type parameter, which I'm going to call dependencies because that's basically what we're representing. And we have to go a bit deeper into variance. By the way, I don't know if you can see, my slides are about this big on my screen, so I'm leaning in to read this. The important thing to note is that the type that is inferred in this after method, which is going to be a consequence of these two parameters here, and will be search.type with source.type, is going to be used to infer automatically, using just the normal mechanism the Scala compiler uses to infer types. It will determine what the type of the env will be by virtue of the way I've implemented after. And we will therefore have an env in scope in the body of type env of search.type with source.type. And when we call source in here, and likewise when we call search.type, these apply methods will look for an env of the appropriate type, which for them, at least for source, will be env of source.type. So they're not identical types, but we have an env of search.type with source.type. We want an env of source.type. And by virtue of that covariance, this is a suitable implicit to satisfy this constraint. So that is good. If we try to access an async value called foo, there is no foo in this intersection. The env that's in scope would not be a valid parameter. And that is a subtyping constraint that the compiler is effectively doing. It's checking whether this is a subtype of this. So it finds it and uses it. And that's part of the story, but there's still the type inference. And you looked at all the types I had to write explicitly in there, and it's much more verbose than the code I showed at the beginning. So we want to the maximum extent possible, use type inference to help us. We want to infer all these types, and this is very much done by the definition of after, which I will, I think, show you now. So this is the signature of after. So it takes var args of dependencies, and we're going to find a type here. The compiler will find the best type which is suitable for all of the parameters that you provide to that after method. It will be instantiated when those parameters are provided. And what the compiler does, which is what it does in all cases, it finds a least upper bound of those parameters. And note here that this same depth, which gets determined here, is then used for the parameter to the lambda. So it finds a least upper bound, and if you remember all of those parameters I provided in the examples, search and source, they were async values. Async of some return type, some input, some dependency types. That's not what we want. That will just give us a value of type async. It won't give us what we need to be able to calculate that nice intersection type that we're then going to use for the env. And it doesn't really give us a handle on that. So we need to do something better. And we're going to use, having already used covariance, we're going to use contravariance. This is the categorical dual of covariance. And it will help fix the problem, albeit with a little bit more boilerplate. But let's look at this for now. So I'm going to change the type of those dependencies in the after method. So here, I'm going to say we want dependency of some type rather than just the sum type raw there. And by virtue of this minus in the type parameter, this will be a contravariant type parameter. And what we can do by wrapping each of those parameters here, source and search, specifying the type as source.type or search.type, the type that gets inferred by virtue of these parameters being provided and the compiler doing what it always does, which is to calculate a least upper bound, under contravariance, that relationship between that subtyping relationship gets reversed. Contravariance flips the relationship. So two types, one of which is the supertype of the other, when they get wrapped in a contravariant wrapper, the supertype becomes a subtype of the other. It flips the relationship. And a related consequence of that is that for that particular type, the lub sort of transforms into a greatest lower bound. It's no longer an upper bound, it becomes a lower bound. And it turns out that the greatest lower bound, for reasons I won't detail, but you can think about and it makes sense, is just the intersection type of all of the parameters, the parameter types. There was lots of boilerplate there, so I want to remove that. And what I can do is use another feature of Scala, which is implicit conversions. And I can arrange things so that if I'm demanding dependency, things that are typed as dependency, my contravariant wrapper for these parameters, and I provide async values, these are the wrong type. They do not match. The types are completely unrelated. But I can provide in scope an implicit auto-wrap conversion. Auto-wrap is just my name, which takes an async and provides a dependency and specifies the type of this to be parameterized on the singleton type of the parameter. What the compiler will do is it will, when you provide a value which is of the wrong type for the position it's provided in, the compiler will go and look to see if there are conversions available that allow it to do the conversion. And it finds this one, and it applies it. And what's really nice is it's able to apply it to all of the parameters to this this varargs after method, and it will then infer the appropriate type that we want. So this will allow us to write the very concise code we wanted and still infer that relatively complicated intersection type that we wouldn't get if we were just doing a normal lub. Now, looking at this more generally, there is a lot of syntax that gets hidden by that we don't need to write, that is inferred. So this rather ugly set of page of code here gets converted into something that is much cleaner, much more boilerplate free. And this is what you write. The previous slide was all the things that the compiler will work out for you. I think that's quite nice. What I don't like so much, I say this is almost boilerplate free, is we have lots of implicit envs here. These are the same every time, so I consider them boilerplate. The solution doesn't exist in the current Scala compiler, but the next generation Scala language, which is based on the Dotty compiler, does allow the concept of implicit functions. And these allow us to move the definition of the implicitness of that parameter to the lambda from the call site to the definition site. And when it's in the definition site, we don't even need to specify that it is a lambda, that it has that parameter. The compiler simply knows that it must exist. It's able to infer from that there is an implicit that will be in scope for the body, for the thunk that you provide to that async constructor. And this gives us basically what we want. So in Dotty, this would be the relatively minimal code that we would need to write in order to define that. I think that's quite nice. The only real repetition is that we have had to define search and source both as dependencies and in the body. But I think it's useful sort of account keeping to explicitly declare them. And if we don't, of course, it is a compiler error, because that was our main objective. So that's what maybe we will have when Dotty is available in a couple of years. I do want to look at the implementation, although I find types much more interesting than runtime values. I generally write the types first for any program, and then if the types all compile and I don't have to do any horrible casts, then I can be reasonably sure that the runtime implementation is correct if the types all line up, and I know that things are not doing nasty tricks behind the scenes. The implementation is basically one line. I sequence all of the dependencies, which are defined as parameters to that after constructor, and then I map the body of the async across them. It's a single line of code. By virtue of this being a lazy val, the calls to the futures here, that may result in those futures calling things and those futures calling things up the tree that arises from any particular node in the graph. And then we can call the action. Remember, the action is still a lambda. It's a lambda from an env to some return type. We can call it with any env at all. Just a single instance of env will actually satisfy all of them because it's just evidence. We don't need to use it. We don't need to construct a new env value every single time. So we provide this consistent object every single time, and it's fine. It works. And then the definition of the apply method here, this is where the danger lies, because we have these calls to get.get. Again, ignoring exceptions, the only thing that's unsafe here is that the futures that this depends on may not have completed. But what we've done is we've encoded in the type system that this can only possibly be run by virtue of demanding this env instance here, if we are guaranteeing those futures have completed. So this is the risky line, and I'm arguing based on the code here that it is nevertheless safe. Now, if I can have if I can have all my danger channeled through this one particular call, that's much better than having lots of dangerous calls all over the place. If I can learn to trust this one, then I'm much happier than having to trust a large surface area of dangerous calls. So that's quite nice. I'll give you a very quick example that I'm applying it to a testing scenario. So say you're doing some testing. You want to test test putting some records into a database. Nothing very exciting. Again, it's a little bit trivial, but when you're writing tests, they often need to depend on other values. And some of those tests can be done in parallel, other ones can't. So here, what we want to be able to do is download a file. I'm going to go to that wonderful website, example.com, and get data.csv. And I'm going to download it and test that this is a reasonable length, the one we expected. And after I've connected to the database, this is another. I started in the middle there, didn't I? After I've connected to the database successfully, I can create a table in that database here, depending on DB. I need to call DB here in order to access that database connection. So this is a dependency. We can't attempt to do this until we've got that database connection. But it's completely fine to be doing this, to be downloading the file while we're connecting to the database. So we've got parallelism here. And I'm declaring these things in sort of whatever order feels reasonable. But by virtue of the way or the checks the Scala compiler does, they do need to be in an order where I can only refer to things that have been declared above. This is actually quite a useful way of preventing cycles happening in our code. So I can't have one thing refer to something which refers back to the other thing. I can't have forward references. And it's quite nice that a constraint the compiler enforces upon us is pretty much isomorphic to a constraint we want to have on a dependency graph. We don't want to have cycles. We want it to be acyclic. And the compiler is simply not letting us write code which would result in that for a reason that maybe seems a little bit unrelated. But the constraint the compiler enforces on us is simply because it can't calculate a recursively inferred type, and it can't forward reference things that haven't been instantiated yet. So given how long have I got?
Last.
Yeah. Okay. So just to finish off this example and summarize, we can do some more things. We finally print the test, and we sort of you can check the slides online later, but you can follow this example through, and it has parallelism where it can take advantage and doesn't where it can't, obviously. And just to quickly summarize, Impromptu is available. It's open source. It's on my GitHub account. The most remarkable thing maybe is that it's only 30 lines of code. All of that complex typing fits into 30 lines of code. It's Apache licensed. There's a binary available. That is the entire source code for the library on one slide. And that is a useful point to finish. So thank you for listening. I'll be around for the rest of the day. Ask me about this. Ask me about Magnolia. Anything else that I've done. And
yeah. Thank you, John. This is really sexy. I guess we have time only for one more question. Yeah.
Okay. Yeah. Do you want to wait for the mic?
Hey, John. Thanks for presentation. And I looked at the code present on the slides, and I noticed that so far it only requires parallel action, so it could be like abstracted away probably in using applicative type class, not just being dependent on futures. Can it be done? Have you tried exploring some of this?
No, but I've thought about it. So it's currently applied to futures. That's hardwired, but it would be nice to abstract over it with a traverse. So the future.sequence is a traversal.
It's traversal on lists. It's always available.
Sorry, say that again?
It's like a traversal on lists. It's always available.
Yes.
You require applicative on the monad. Or on the type
so it might be interesting to do it with other things that for which the type classes exist. We need a functor to map over the result of that. And then there's some sort of concept that makes it useful, which is that there is, at least for future, there is a potentially dangerous call to get that should only be applied in the cases where it makes sense. But this is this I think is the way to abstract over it. Yeah, and by pulling in 2 or 3 type classes, that one-liner that was at least in the version you saw, lazy val future, that could be written in a more generic way, and I think that would be a nice way to provide more generic graphs of things, and the interpretation of those is maybe very interesting. So
thank you very much.
Thank you.
Thanks.